Imagine a place in the vast, silent theater of space where nothing can run away, not even light, the fastest thing we know. This place is a black hole. One of the most mysterious and powerful objects the universe can create, a region of complete darkness, a quiet void against distant stars. Thinking about it stirs a deep curiosity within us. It is a place that challenges our understanding of reality, a silent enigma that pulls matter and our imagination into its depths. Its existence forces us to ask about the fabric of space and the flow of time itself. A black hole is not a roaming monster. Instead, a static, powerful presence defined by immense gravity. A black hole is born from an ending. It begins with a star, a massive one, far larger than our own sun. Throughout its long life, this star shines brightly, a brilliant beacon in the darkness of space. It is a giant furnace, constantly converting matter into energy in its core. This outward push of energy balances the inward pull of the star's gravity. For millions of years, the star stays in equilibrium, a stable, radiant sphere. But this state cannot last forever. The fuel that powers the furnace is finite. Eventually, it begins to run out, setting the stage for a spectacular, final transformation. When the fuel is gone, the outward pressure from the core suddenly stops. With nothing to hold it up, the star's massive outer layers come crashing down. The core collapses under its own weight in a fraction of a second. This implosion is so violent it creates something entirely new. Every black hole is surrounded by an invisible boundary. This boundary is not a physical surface you could touch, like the ground. It is a threshold, a line drawn in space itself. Scientists call this boundary the event horizon. It marks the point of no return. Imagine it as the edge of a waterfall on a perfectly calm and wide river. Before you reach the edge, you can still turn your boat around and row back to safety. But once you drift past that edge, the current becomes too strong, and you are inevitably carried over the falls. The event horizon is the cosmic equivalent of that waterfall's edge. From a great distance, the event horizon appears as a perfect sphere of blackness. It is the shadow the black hole casts upon the universe. Any light that crosses this boundary from the outside is trapped forever, and any light that might be emitted from inside can never reach us. This is why the object itself is black. However, the area just outside the event horizon can be one of the brightest places in the universe. Gas dust stars. As you get closer to a black hole, the laws of nature begin to behave in unfamiliar ways. The immense gravity doesn't just pull on you, it pulls differently on different parts of your body. Imagine falling feet first toward the black hole. Its gravity would pull more strongly on your feet than on your head because your feet are slightly closer. This difference in gravitational pull would create a stretching force, pulling your body apart. Scientists have a name for this effect: tidal forces. For smaller black holes, this stretching force is incredibly powerful. It would stretch any object into a long, thin string of atoms long before it reached the event horizon. Near a supermassive black hole, the experience would be gentler at first. Because these black holes are so large, the event horizon sits much farther from the center. The curve of space-time is less sharp at the edge. An astronaut might be able to cross the event horizon without being immediately torn apart. Light itself is not immune to the black hole's influence. Near a black hole, this bending is extreme. This phenomenon is called gravitational lensing. According to Einstein, time can slow down. The stronger the gravity, the slower time passes. If you could hover in a spaceship just outside the event horizon for an hour, then return to Earth, you might find that many years had passed for everyone back home. Despite their mysterious nature, there are many things that scientists know for sure about black holes. First and foremost, we know that they exist. This is not a guess or a science fiction idea. The evidence is overwhelming. For decades, astronomers have watched stars at the center of our Milky Way galaxy, orbiting something they cannot see. By tracking their paths, we can calculate that the unseen object must be incredibly massive, about 4 million times the mass of our Sun, and packed into a very small space. The only known object that fits this description is a supermassive black hole. We also have direct visual proof, a global network of radio telescopes. The Event Horizon Telescope captured an image of a black hole's shadow. The image shows a dark central region, the point of no return, surrounded by a bright ring of glowing gas. The size and shape of that shadow match Einstein's general relativity predictions. Furthermore, we have detected the echoes of black holes colliding. Using incredibly sensitive instruments on Earth, we detect faint ripples in space-time. These are called gravitational waves. We have detected these signals. They act like a cosmic siren, telling us about the masses involved. Black holes come in different sizes. We can observe accretion disks of hot gas swirling in, and powerful jets launched from their poles at nearly the speed of light. While our knowledge has grown immensely, black holes continue to guard some of the deepest secrets in all of physics. The single greatest unknown is what happens at the very center. Our current theory of gravity predicts that all the matter that falls into a black hole is crushed into a single point of infinite density, the singularity. At this point, our mathematical equations break down and our understanding of physics fails completely. We know that this idea of infinity likely signals our theory is incomplete. A new, more powerful theory is needed to describe what truly happens in this extreme environment. This leads to the black hole information paradox. In physics, a fundamental rule says information about an object can never be truly destroyed. Information is the unique set of properties that describes an object, its mass, spin, composition. But when something falls into a black hole, it seems to disappear forever. So what happens to the information it carried? Does it vanish from the universe, breaking a core scientific principle? Or is it preserved on the event horizon or encoded in the faint radiation black holes are theorized to emit? We also wonder what the experience of space, and of time, is truly like inside the event horizon. Do space and time swap roles, as some equations suggest? Could a black hole be a gateway to another part of our universe, or even to another universe entirely? Could primordial black holes be much smaller and even make up some of the dark matter? These unanswered questions are not failures of science. They are the frontiers that drive us to look deeper. Once an object crosses the event horizon, it enters a part of the universe that is fundamentally cut off from us. What happens next is a journey into pure theory, guided by mathematics, but without any possible confirmation from direct observation. According to our current understanding, the journey onward is swift and final. For an astronaut who crosses the edge of a supermassive black hole, the outside universe would appear to speed up dramatically. They would see stars and galaxies age, die, evolve in what feels like mere moments, a final fleeting glimpse of all of cosmic history. Inside the event horizon, space and time themselves are thought to behave in a profoundly distorted way. Inside a black hole, it is believed that all possible paths in space lead in only one direction, toward the central singularity. Just as we are powerless to stop the flow of time, an object inside a black hole is powerless to stop its fall toward the center. The tidal forces that were gentle at the event horizon of a supermassive black hole would grow unimaginably strong. Any object, a spaceship, a planet, or a person, would be elongated and compressed into a thin stream of fundamental particles, in a process sometimes called spaghettification. Our journey to understand black holes is a testament to human ingenuity and the power of our scientific tools. Since we cannot go to a black hole ourselves, we must build extraordinary instruments to bring the black hole's environment to us. Optical telescopes. Radio telescopes. They gather the faint light and radio waves from matter swirling around black holes. By studying the spectrum of this light, we can learn about the temperature, speed, composition of the gas in the accretion disk. These observations give us clues about powerful processes just outside the event horizon. To photograph a black hole's shadow, scientists created a telescope the size of the Earth. The Event Horizon Telescope is a network of radio observatories across the globe. By combining data with interferometry, astronomers create a virtual telescope with astonishing resolving power. This tool let us peer 55 million light-years and capture the silhouette of the supermassive black hole in M87. Another revolutionary tool lets us listen to the cosmos. LIGO and international partners detect the faintest vibrations in space-time with lasers shot down long perpendicular tunnels. When a gravitational wave from two black holes merging passes by, it stretches and squeezes space, changing the distance the laser beams travel. Powerful computers model matter, light, and space-time near black holes, letting us test Einstein's predictions and compare them with real observations. By creating virtual universes, we experiment with scenarios and interpret data, guiding our search for answers to the remaining mysteries. In the end, the black hole remains a profound duality. It is both a known object, cataloged, observed, and a deep, fundamental mystery. We can describe many of its external features with confidence. We can watch how its gravity choreographs the dance of nearby stars and gas. We can even capture its faint shadow against the bright background of the cosmos. Our theories have been proven right time and again outside the event horizon. These successes are a triumph of science. Yet the true nature of a black hole's interior remains veiled. The singularity, the fate of information, the very structure of space and time inside the event horizon, profound puzzles at the foundations of reality. They remind us the universe will always hold new challenges and deeper layers of complexity. So, what really happens inside a black hole? For now, the final answer lies beyond our reach, hidden behind a one-way door in space-time. The black hole remains a silent teacher. It does not give up its secrets easily.